All right, everybody. Got a spectacular 2D motion problem. This one is about Alan Shepard. Alan Shepard was the first American to go into space, and he was the fifth person to walk on the moon. He is somewhat famous for making a makeshift golf club, taking a golf ball, and hitting it on the moon. And when he hit it, apparently, he's quoted as saying it went for, quote, miles and miles. So let's explore what it was like for Alan Shepard to hit a golf ball on the moon. So in our problem, he's launching it at a 45-degree angle, and we know it goes 4.83 kilometers, 4.83 kilometers in 77.2 seconds. And we want to know two things. What was the initial velocity in this 45-degree direction that he hit it with? And what is the y max? The highest height that the ball gets to. Okay. So we're going to have to use this information somehow, this distance and this time. Now, since we know that there's no acceleration in the x direction, I can use this information to find out what my velocity in the x direction would be. What I mean is v naught x equals, converting to meters, 4,830 divided by 77.2. I'm taking the x displacement over the total time. And since the acceleration is 0 in the x direction, I know that this will be the constant x velocity throughout. And this, I get 4,830 divided by 77.2 equals 62.6 meters per second. But I also know I have another equation to figure out my v naught x, my initial velocity in the x direction. I can use my trig rules to compare that to the true absolute velocity in this 45-degree angle direction. What I mean is, remember v naught x equals v naught times the cosine of 45. So v naught equals this answer divided by the cosine of 45, 88.5 meters per second. So this is how fast it was hit in that diagonal direction. That's our first answer for this one. So now I think the best way to do the y max, well, the way I would always do it is to express vy as a function of t. And this equals v naught y minus at, which for the moon, the acceleration due to gravity is going to be 1.62. So I can write this as 88.5 times the sine of 45 minus 1.62 t. But I know that at t max, which is the height when the ball reaches its max height, vy of t equals 0. Right? The ball has reached its max height and it's starting to turn around. So for a brief moment there, the velocity in the y direction is 0. So I can solve t max must be equal to just setting this equal to 0 and solving, equals 88.5 sine of 45, all divided by 1.62. And this equals this answer divided by 1.62 times the sine of 45 equals 38.6. And you'll notice that it's half of our total flight time. That's what we expect. So then y max equals y evaluated at this special time, t max. So then y max equals, well, I can express y of t equals v naught yt minus gt squared over 2. So y max equals evaluating this thing at this time. So I will get 88.5 times the sine of 45 times 38.6. Here, gonna need some more room. So here's my y of t. So y max equals y evaluated at 38.6, which is my max time. And this equals 88.5 times the sine of 45 times 38.6 minus 1.62 over 2, and then I'm just going to write it as T max squared. And I will get 88.5 times the sine of 45 times 38.6 minus 1.62 divided by 2 times 38.6 squared, and I get 1,208 meters. So we started out with our x information. We had some displacement and some time. We used that to find our x velocity. We used our trig rules to find the actual initial velocity in this 45-degree angle direction. And then now that we have this initial velocity, we can start dealing with the y direction. I express my y velocity like this. We know that at this max height, my velocity in the y direction must be 0. So I can solve for what time that is. And then we know that the max height is just evaluating y at that special time. And we get 1208. And that will be your solution.